Hello friends, I'm Rajneesh Kumar, working as assistant professor in NIT Pharmacy Institute, Greater Noida. So I'm here again in front of you with the continuation of the previous lecture. In the last lecture we have discussed the structure, synthesis and usage of naphthalene. So again, as it belongs to the pharmaceutical organic chemistry of third semester of B.Pharm program of AKTU. So in this lecture we have discussed about the phenanthrene. Now our focus will be on the structure and synthesis of the phenanthrene. Okay. So without any delay, I'm just coming to the point. So as you can see that phenanthrene is a polycyclic aromatic hydrocarbons composed of 3 benzene rings. Okay, 1, 2 and 3. Okay, so in its pure form it is found in cigarette smoke and is a known irritant photosensitizing skin to the light. So it's a very toxic, but the toxic studies on the human beings is not reported till now. So phenanthrene appear as a white powder having blue fluorescence. Phenanthrene is the backbone of the morphine. So as you can see there, the structure of phenanthrene having mainly 3 benzene rings which are fused together in the angular fashion. So it is different from the anthracene, as in case of anthracene all the 3 benzene rings are fused in the linear fashion. So you can call it as the isomer of the anthracene. Both the anthracene and phenanthrene having the 3 benzene rings. The only difference is the joining of benzene ring together. In case of anthracene it is linear joining of 3 benzene rings, but in case of phenanthrene it is angular joining of the benzene rings all together. So now when we are discussing about the structure of phenanthrene, so you can see there you can draw the structure of phenanthrene in 2 ways. The one is, as you can see there, this is ring A, B and C. While जब हम rotate करेंगे bonds को, then it may be written as this line. So while we going to nomenclature the phenanthrene ring, so just remind, हमको ये ध्यान रखना है that it will always started from the terminal benzene rings, either this one or this one. Okay, so in case there we have started 1, 2, 3, 4, 5, 6, 7, 8 and then 9 and 10. In case of this structure we have started again from this way 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So and phenanthrene should be nomenclature like this, numbering should be done like this. Again, when we are talking about the isolation of the phenanthrene, so it is isolated from the green oil fraction of the coal tar. So after fractionation distillation, after fractional distillation, the whole portion is undergoes cooling. After cooling, that particular portion will give us precipitate. That precipitate will be treated from the naphtha solvents. So after naphtha solvent, phenanthrene along with other similar products will be precipitated out, which will be again washing with the picrate. So washing of the with the picrate is required because phenanthrene is the only product in this mixture which is soluble in the picrate. The other impurities is not soluble. So after washing with the picrate, the whole portion will be filtered out, and after that filtrate will be crystallized out and pure phenanthrene will be collected. Okay, so this is the major way to get phenanthrene. Now before going to the other things, we have just discussed in detail about the structure of phenanthrene. So as you can see there, the molecular formula of phenanthrene is C14H10. So the formula itself indicate that it is a highly what, like benzene, it is aromatic compound and unsaturated, highly unsaturated compounds, because number of carbon is more than the number of hydrogen. So okay, then I have already told you that it is isomer with the anthracene. Okay, because both have the benzene rings, 3 benzene rings fused together. The only difference is the way of joining the benzene rings all together. Then on oxidation phenanthrene, it gives phenanthroquinone, which on further oxidation gave diphenic acid. So when we go for the establishment of the structure, or you can say that structural elucidation of the phenanthrene, the first thing we have to do is elemental analysis. So after doing elemental analysis, this structure, this formula of the phenanthrene is confirmed, which tells about the you can say that aromaticity and the highly unsaturated nature of phenanthrene. Then now again, for establishing the proposed structure, we have to go for some chemical reaction, which again help us to establish the structure, because the product which will be formed after the certain chemical reaction is supported to the proposed structure of the phenanthrene. So as you can see that phenanthrene, when undergoes oxidation, we are getting phenanthroquinone. Again, that phenanthroquinone further on further oxidation will give diphenic acid. So as we are getting diphenic acid as the oxidative product, so it is again confirmed that there is at least two benzene rings are present in the structure of phenanthrene. Now after getting diphenic acid, we just react diphenic acid under the reaction of decarboxylation. So we react this diphenic acid with the soda lime, and decarboxylation means the removal of carbon dioxide. So as a product we are getting diphenyl. So because this diphenyl as a product we are getting after the decarboxylation of diphenic acid, so it clearly indicates that phenanthrene must contain the following structure like this, because two benzene rings are there. Okay. So if two benzene rings of phenanthrene is not there, we are not getting the diphenyl as a product. So this clearly indicates the structure of phenanthrene should be like this. It is having two phenyl rings which are joined together, and at the ortho position there should be two carbons are also there. Then again, now on closing the middle ring and filling the hydrogen to satisfy the valencies of various carbon atoms, phenanthrene get the following structure. So like you see in the previous slide, if we are just thinking about the structure of phenanthrene, so again there is a problem of the valency of the carbon, which can be removed by just closing the ring. So after closing the ring, to resolve the problems of all the valencies of the carbon, we are getting this structure of phenanthrene. Okay. So this structure of phenanthrene is also established, and lot of evidence can also be there for the support of that phenanthrene structure. So when we go for the identification of the different substituted product in this phenanthrene ring, so we found that it gives 5 monosubstitution and 25 disubstitution derivative. So it again clearly indicated that phenanthrene is the phenanthrene is having this particular structure. Now, so this is all about the chemical and synthetic evidence in the establishment of the structure of phenanthrene. So now the most important thing of any polynuclear hydrocarbons are the its orbital structure. So as you can see that there is a like this. This is phenanthrene. Okay. So as you can see there, each carbon, it is having 14 carbon and 10 hydrogen. Each carbon is having 4 valency. So 3 of the 4 valency is satisfied by making a bond with the hydrogens and other 2 carbons in the ring, while 1 valency is having unhybridized p orbital, which is having 1 unshared electrons. Okay, that unshared electrons will be perpendicular to the plane of the phenanthrene ring. Means like benzene and naphthalene, it is also having planar structure, and that planar structure, in that planar structure each carbon having 1 unhybridized p orbital, which is having single electron. Because of that electron, the electron cloud above and below of the plane of phenanthrene is there. Because of that, nucleophilic substitution reaction is not possible in case of phenanthrene. The only possible reactions along with oxidation and reduction is electrophilic substitution reaction, because a electron cloud is present in above and below the plane of the phenanthrene ring. Okay. That sp2 orbitals overlap with each other, and as I said you that the sp2 orbitals overlap with each other and with s orbital of the 10 hydrogen atom to Cc and the CH bond. So, because of that bonding, that all the 14 carbons having fulfilling their 3 valency out of 4, 1 valency is fulfilled by the one unshared unhybridized p orbital, which is having single electrons. So, each carbon atoms also possess p orbitals, and these are perpendicular to the plane containing the bonds. The lateral overlap of these p orbitals produce p molecular orbital containing 10 electrons. So, again I am just drawing it. So, it is having like this. In all the 3 rings, and these are overlapping with each other laterally. So, because of that lateral overlapping of the p orbital, electron cloud will be formed below and above of the plane of phenanthrene ring. Because of that electron cloud, electron substitution reaction will take place in case of phenanthrene. Now, phenanthrene shows aromatic property because the resulting molecular orbital satisfied the Huckel rules, n is equal to 3. So, as you can see there are 1, 2, 3, 4, 5, 6, 7. Okay. 7 double bonds are there in case of phenanthrene. The total number of pi electrons are 14. So, as per the Huckel's rule, 4n plus 2, so n is equal to 3. Okay. So, as per the Huckel's rules, n is the integer number. So, this structure of the phenanthrene satisfied the Huckel rule also. So, again, if we are talking about the resonance in case of phenanthrene, so we have to just delocalize the double bond present in this. So, like this, in case of this is structure 1, 2, 3, 4 and 5. So, हमें ये ध्यान रखना है जब भी हम रेजोनेंस स्ट्रक्चर बनाएंगे कि कोई भी स्ट्रक्चर रिपीट ना हो. सपोज नाउ यहाँ पर हमने क्या किया, हमने यहाँ पर डबल बॉन्ड का डिलोकलाइजेशन कराया, इस बॉन्ड को हम लोगों ने यहाँ मूव कराया, इसको यहाँ मूव करा दिया, इसको यहाँ करा दिया, लाइकवाइज, एंड वी आर गेटिंग सेकेंड स्ट्रक्चर ऑफ द phenanthrene. सो यहाँ पर हमने जब डिलोकलाइजेशन कराया डबल बॉन्ड का, वी हैव गॉट 5 रेजोनेंस स्ट्रक्चर ऑफ द phenanthrene, which can so phenanthrene can also be put like this. It is the resonance hybrid of all these 5 resonating structure of the phenanthrene. So, now come to the one by one. So, in case of first structure, you can see that this ring and this ring, these 2 rings of 3 having the whole of saxhlate, these are means 2 rings out of 3 have the benzonides nature. Okay, they are the benzene rings. They are have completed saxhlate in the structure. Now coming into the second, here only 1 ring have the saxhlate, complete saxhlate. Here again there is 2 ring having the complete saxhlate. Again this is having 2 ring with the complete saxhlate, and here again having 2 saxhlate. Okay, so I mean to say that the resonating structure which is having more benzene ring with the aromatic saxhlate complete will participate more in the structure of benzene. Okay. Again, resonance energy of phenanthrene is very high, because out of 5 resonating structure of the phenanthrene, most of the structure is having aromatic saxhlate in 2 ring out of 3. Okay. So, as you can see that resonance energy of phenanthrene is very high, means it is very stable. Again it is flat molecule, as we have discussed already, because it is having 14 carbon and each carbon having sp2 hybridized carbon. Each carbon is sp2 hybridized, okay, and one p orbital hybridized p orbital is there with the unpaired number of electron. So the existence of resonance in phenanthrene is provided by the following facts. Resonance energy is very high, so it is very stable. It is a flat molecule. Then X-ray diffraction studies show that all the CC bonds in the phenanthrene are not equivalent. Means if we go separately one by one, then we have see that the C1 C2 carbon, the bond in between the first carbon and the second carbon, has 3/5 double bond character, while the bond in between carbon number 2 to carbon number 3 has 2/5 double bond character, while in case the bond in between carbon 9 and carbon 10 have 4/5 double bond character. So you can say that there is difference in the double bonds nature of the phenanthrene. Now finally this structure, the proposed structure of the phenanthrene, is also confirmed by the synthesis of the phenanthrene. So I am taking here the example of Howard synthesis. So in case of this synthesis, we are taking naphthalene and succinic anhydride as a reagents. So both the reagents are reacted in the presence of Lewis acid like AlCl3. So you know that succinic anhydride is the acetylation is occurring, and we are getting 4 naphthalene, 1 aryl, 4 oxobutanoic acid. So what's happening actually? One of the H, this, okay, it will react with one of the oxygen, okay, and this bond will be break, and we are getting this carboxylic acid derivative as a product. Now what happening now? So you can see that we are using zinc, amalgam and HCl, means we are going for the reduction of what? Reduction of this carbonyl group. This carbonyl group, CO group, is changed into the CH2 group. So first of all, we have performed acetylation in the presence of AlCl3, then we go for the reduction in the presence of zinc, amalgam and HCl, okay, and after reduction we have got 4 naphthalene, 1 aryl butanoic acid. Now this product will be treated with the concentrated H2SO4. So we know that H2SO4 is a very strong dehydrating agent. So after reacting with H2SO4, 1 mole of the water is removed, and we are getting another intermediate. So this intermediate named is 3,4-dihydrophenanthrene 1,2H on. So again we are having 3 benzene, 3 ring, out of 3 ring to our benzene ring, one is cyclohexane ring, which is having keto group, okay. So if we are going for the synthesis of phenanthrene, so we have to convert this ring into another benzene ring. For what we are going, for that we are going again for reduction. So in the presence of zinc amalgam and HCl, this keto group is reduced, and we are getting 1, 2, 3, 4 tetrahydrophenanthrene, and again reduction is done, okay. Means the hydrogen, 4 hydrogen molecule atom will be removed in the case of selenium and palladium, in the presence of selenium and palladium, and we are getting phenanthrene as a product. So this synthesis is also very strongly supported the proposed structure of the phenanthrene, okay. Now come to the synthesis of phenanthrene again. So again we are having very important reaction like Howard synthesis, which we have also used for the also used as evidence for the structure of phenanthrene. So again I have already discussed it. So you can see that in the first step Lewis acid like AlCl3 will be used to perform the reaction. In the second step reaction is done. In that particular step the carbonyl group is removed to the CH2 group. In the next step cyclization occur because concentrated H2SO4 will be used and 1 mole of the water will be removed. In the next step again we are going for a reduction. in the next step again we are going for the oxidation, you can see, okay, because hydrogen will be removed, okay, in the presence of selenium and palladium, and we are getting phenanthrene as a product. So the next important synthesis of the phenanthrene is Pochette synthesis. So actually this is very important synthesis because we are using diazotization reaction in this particular synthesis of phenanthrene. So what we are doing that actually we are also using two parts mainly. Actually this reaction is having, one is Perkin reaction, this is the part of Perkin reaction, okay. So you know that in case of Perkin reaction we are getting alpha beta unsaturated carboxylic acid or carbonyl compounds. So we are also required acetic anhydride, salt of sodium salt of acid, and we are having one aldehyde. So the one aromatic aldehyde is reacted with aromatic carboxylic acid salt in the presence of aliphatic anhydride. It's a Perkin reaction, example of Perkin reaction, and we are getting derivative of cinnamic acid, okay, in the first part. That particular cinnamic acid is also an example of the alpha beta unsaturated carboxylic acid. Now we have to prepare this structure, actually phenanthrene. So for that this NO2 group will be reduced to the amino group. How? We are just again using zinc amalgam in the presence of HCl. So this NO2 group is changed into the amino group, okay. So now we are having a molecule which is having free amino group. So we are going for the diazotization reaction, okay. So as you can see there, we are using NaNO2 and HCSO4, and there should be temperature should not be rise above 5 degrees centigrade. If temperature should not be kept under 5 degrees centigrade, then diazotization will not be taken place. So the most important precaution we have to take is the maintenance of the temperature in that particular step. So as we know already that this NaNO2 is directly not reacted with the molecule. Actually this NaNO2 and H2SO4 will reacted together, and there is a production of, or there is a generation of nitrous acid HNO2, okay. That nitrous acid will be reacted with this amino group, and we are getting this molecule here. 2 nitrogen like this is present. This is diazotized product as a intermediate. Again, when this product is heated in the presence of copper, we are getting phenanthrene as a product. So this is again very important synthetic scheme for the synthesis of phenanthrene. Now the other method for the synthesis of phenanthrene and its derivative involves again this is a derivative of phenanthrene, quinone. This product can be produced in the Hoover synthesis. You can see there after the cyclization with H2SO4 we are getting this product, and in the next step we are going for the reduction of that carbonyl group. So from that step of the Hoover synthesis, this molecule will be taken out and it will be reacted with the Grignard reagents and water, and we are getting a product which on the reaction of selenium gives substituted phenanthrene, okay, one substituted phenanthrene, okay. So again the next method is also involves some step of the Hoover synthesis, as you can see there. Here cyclization is done, then reduction is done, okay. So here what is the difference in between the Hoover synthesis and this reaction? We are using alkyl substituted succinic anhydride in that particular reaction, okay. The whole process will be same except this reagent. Here we are using substituted succinic anhydride in place of succinic anhydride only. So by this way we can also prepare 2-alkyl phenanthrene substituted 2-alkyl phenanthrene molecule. So this is all about the synthesis of phenanthrene. Now So I'm again focusing on the structure of phenanthrene one by one. So as you can see there, this is the structure of phenanthrene. Again, this is okay. So this is the structure. So I have already told that each carbon is sp2 hybridized, means there are 4 valencies, 3 valencies fulfilled by that, like this carbon we are talking about. So 1, 2 and this 3 valencies fulfilled like this, and this is having unshared p orbital which is having single electrons. Okay. So this p orbital is perpendicular to the plane of phenanthrene, each carbon having, because of that, and after that it will be laterally overlap with each other. So because of that, each phenanthrene ring having electron cloud above and below the plane of the phenanthrene ring, this may be the region phenanthrene easily go for the electrophilic substitution reaction along with the oxidation and reduction. Okay. So the other thing is, okay, so it may be obtained along with the, so isolation, I can again talk for the isolation. So first of all, green oil fraction, cool, solid, precipitate, washed with naphtha, solvent, again filter. It is having the filtrate is having phenanthrene along with the anthracene and other like molecules. Okay. So again, now this filtrate is again picrate से इसको हम रिएक्शन करेंगे. So picrate is having the characteristics that it will dissolve on the only the phenanthrene ring, not the other. So again we will go for the filtration, and this filtrate is having only phenanthrene ring, which on the crystallization gives pure phenanthrene ring. Okay. So this is all about the synthesis and the structure of the phenanthrene ring. So thank you so much.